Welcome back to my YouTube channel. In the course of this video lesson, I'll be teaching on a very important aspect of chemistry, which is called the states of matter, specifically discussing about gas laws. This particular topic is very important for students preparing to write the Jamb exam, the post-UTME examination, or even if you are in your first year in any university. This video lesson is for you. Now, in this topic, which is called the state of matter, specifically the gas laws, from introductory chemistry, we all understand that chemistry has to do with the study of the composition, properties, uses, and structure of matter. Now, on this, what is matter? Matter is anything that has mass and occupy space. We have different aspects to which matter can be classified. We have the state of matter and also we have the forms of matter. On the state of matter, which we are discussing about in the course of this video lesson, we have to understand that we have two major groups of the state of matter, which include the major state of matter and also the minor state of matter. On the major state of matter, they are divided into three, which include solid, liquid, and gas, which we'll be talking about in the course of this video lesson. And on the minor state of matter, they include plasma, Bose-Einstein condensate, fermi-ionic condensate, and lastly, quark-gluon condensate. But in the course of this video lesson, we'll be specifically talking about gas laws, but we have to understand the properties of these gases. Now, from introductory chemistry, we have to understand that gases are states of matter, yes, and also these gas or gas particles in general, they have some unique characteristics, and one of them is that they undergo a type of motion. That is how they move. They undergo a type of motion called random motion. Okay, this is the type of motion that is exhibited by gases. Okay, it is called random motion. If we don't call it random motion, we can as well just say zigzag motion. This is also regarded to be called random motion, or if we don't have to call it zigzag motion, we can as well lastly call it Brownian motion. So these are the type of motion that is exhibited by a gas particle, and this is one unique property of gases. Okay, this must be noted. There are so many. Okay, another is, you already know that the particles of gases are held together by a very weak force of attraction. This is another unique property of gases. Are you following me now? The particles of gases are held by a very weak force of attraction compared to solid. Solid particles are held by a very strong force of attraction. Are you following me now? So, in general, moving further, we have to understand that gases exhibit they have some behaviors. Yes, they exhibit some behaviors. And the behavior of gases, they are described by some variables. This is where I want to start from. The behavior of gases are described by some variables. What are these variables? If I don't want to call them variables, I can as well call them parameters. So the behavior of gases are described by some variables. What are these variables? They include, number one, volume. Volume is the first variable that describes a gas behavior. Another variable is what we call pressure. Pressure is another variable that can describe the behavior of a gas. Another variable is what we call temperature. Temperature is another variable that describes the behavior of a gas. And lastly, number of moles. Number of moles is another variable that describes the behavior of a gas particle. So moving further, this must be noted. We have to understand that volume is symbolized as V. We note that. Pressure is symbolized as P, temperature is symbolized as capital letter T, and number of moles is symbolized as N, small letter n. So all of these are the variables that describe or help to determine the behavior of a gas. We've talked about some of the behavior exhibited by gases undergoing this type of motion, the particle being held by a very weak force of attraction. Okay, now all of these must be noted. So moving further, let's talk about each of these variables. So moving further, let's talk about the first variable, which is volume. So on volume, we have to understand that the space occupied by a body, but since we are talking about chemistry, I'll use the word substance. The space occupied by a body or a substance is regarded to be called the volume of that particular substance. I believe you are following me. But most importantly, you have to understand the units to which volume can be expressed, because it will help us in the course of this video lesson. It will help us in the course of this topic, which is gas laws. So there are various units to which volume can be expressed. They include centimeter cube. Okay, they include decimeter cube as well. They include liters. Okay, they include milliliters, and lastly include meter cube, which you are seeing on the board. We have various units to which pressure can be expressed as well. And what is pressure? Pressure is simply the force exerted by the walls of a container. That is pressure. But most importantly, we have to know the units to which pressure can be expressed. And pressure can be expressed in different units, like number 1, ATM, which is atmosphere, not automated teller machine. We have another unit which we'll discuss exhaustively on, which is mmHg, millimeters of mercury. We have another possible unit pressure can be expressed in torr, which is torricelli. Another unit to which pressure can be expressed is bar. Another possible unit pressure can be expressed is Newton/m squared, which is pronounced as Newton per meter squared. And the last unit to which pressure can be expressed can be Pascal. Pressure can be expressed in Pascal. This must be noted. So temperature, basically in studying gas law, we have to understand two important units of temperature. And the first one is degrees Celsius. We must understand the conversion, degrees Celsius, and another is Kelvin, or we can as well call it absolute Kelvin. So these are the units to which temperature can be expressed, and it's going to help us. We have various units like Rankine scale, expressing temperature in Rankine scale, or even thermocouple. Okay, that's in physics. Okay, but these two units, understanding their conversions is very important in studying gas laws. And lastly, numbers of moles, which we'll talk about, which is a very important concept in chemistry. I already have video lessons on this aspect, which is mole concept, so it's important you watch that video. The link will be in the description of this particular video. So moving further, let us learn. We've already seen that these are the, these basically are the parameters of the variable that help to describe a gas behavior. So let us basically understand the conversions between these variables, because it will help us to solve questions under this aspect, which is gas laws, when we start each of the laws. Okay, so make sure if you're watching this video for the first time, if you are seeing this page for the first time, do well to click on the subscribe button to my channel, and also share my video lessons with your friends. So let us progress. Okay guys, moving further, let us move over to the conversions of the aforementioned variables. Remember, we listed out the variables that describe a gas behavior, and the first one we talked about was volume. So now let us understand how this volume, which we explained to be the space occupied by a body. So let us now talk about the possible conversions. How do we convert this volume when we see them in the gas laws, which we'll explain very soon? So we have to understand that 1,000 centimeter cube, which is 1,000 cm cube, is same as 1 dm cube. This is very important. Okay, and 1 dm cube, which is equal to 1,000 cm cube, is same as 1 liters. Please, these conversion factors are very, very important for you. Okay, and 1 liters is same as 1000 milliliters. Are you following me? And 1000 milliliters is same as 1 times 10 raised to the power of -3 meter cube. So all of these conversions are very, very important. Okay, we'll solve practice question on each of them as we progress in the course of this video lesson. So let me quickly talk about the second, which is pressure, so that we can quickly talk about this aspect and go straight into the gas laws. So on this, let's also talk about the second variable used to describe a gas behavior. Remember, we said that pressure is the force exerted by the walls of a container. So on this, we have various units of pressure which we've seen, and also let's talk about the conversions. So we have to understand that 1 atm, which is 1 atmosphere, is same as 760 mmHg, which is millimeter mercury, and 760 mmHg is same as 760 torrs. Are you following me? Which is torricelli. And 760 torr is same as 101,325 Pascal. And 101,325 Pascal is same as 101,325 Newton per meter squared. And 101,325 Newton per meter squared is same as 1.01325 bar. Okay, and 1.01325 bar is same as 76 centimeter mercury. So I just wrote out all the possible conversion factors for pressure. So whatever unit to which the pressure of volume will be seen in the laws, when we start discussing them, you can actually work your way through. They are all easy. So let's talk about temperature, the other parameter or variable used to describe a gas behavior. Remember, we said that temperature has to do with the degree Celsius scale and also the Kelvin scale. On this, you have to just know this formula, which is degree Celsius plus 273 is equal to Kelvin, because most of the time they give us temperature in question in degrees Celsius. So what do? We must convert to Kelvin by adding 273 to our temperature given already when we start solving practice question. So let's give an examples to all these said so we can progress. Okay guys, example 1. For instance, we're given a practice question to convert, for instance, let's say 700 centimeter cube to, let's say, a dm cube, for instance. Very easy, like A, B, C, D. So when you see questions like this, what do? You have to then go back to your conversion table, conversion where the conversion factors was written, but you have to know it inside your cerebrum. Okay, it's very important. So you have to notice. So what am I relating? I'm relating two things: centimeter and dm cube. Centimeter cube and dm cube. So then you have to now bring out, first of all, you go back to that stuff in your head, and then now say, okay, it's between centimeter cube and dm cube. Then what do? I will then write the initial value given to you. The initial value you already know, not the one they gave you in the question. You then write it up. 1000 centimeter cube is equal to what they asked you to convert to, which is what? 1 dm cube. Are you following me? You put that first up. So then I say convert this to this. So then your 700, the guys they give to you in the practice question, that's what you now bring down, and you write it in the same column of the guy up, the guys up. So here was 700, that's why here was 1000 centimeter cube, that's why here was 700. I cannot go and pull something that is not of the same unit underneath it. Do you understand? So 700 centimeter cube is equal to x dm cube, which you are asking me to solve for. So cross multiply. What becomes x dm cube? Simple. When we are cross multiplying, since you are looking for this, you times this first. Okay, you times this. So it's going to be 700 centimeter cube times 1 dm cube. You now then, after you times, you now then divide by what is given. So over 1000 centimeter cube. So centimeter cube will cancel centimeter cube, you leave in just dm cube. So what do we have? 700 times 1 divided by 1000. Okay, divided by 1000, that's 0.7. That's 0.7 dm cube. Do you understand? So it's very easy. Even if they ask us to calculate, it's very easy. Even if they ask us to convert 700 centimeter cube or any number at all to, let's say, milliliters, same thing. what do? It is between centimeter cube and milliliters now. Are you following me now? So you now then it's still the same thing. 1000 centimeter cube is equal to 1000 milliliters. So 700 centimeter cube will now be equal to X milliliters. Hope you are following me. You cross multiply and get your answer. Same approach. It is very easy. Are you following me now? So this is how it's done. So moving further, let us talk about the pressure. It is still the same approach. Let us say, for instance, we are given a practice question to convert, let's say 700 mmHg. I like using 700. I don't know why. Okay, but that's it. 700, you can put anything, no. 700 to, let's say, ATM, for instance. You are relating ATM and this. Do you understand? So first of all, you bring what you already know up. Down first. 760. Okay, you already know that 760 mmHg is equal to 1 ATM. That's what you already know. Then you bring what they get to you down. Okay, here is 700. Remember I said that they should be together. Okay, it's equal to X ATM. Do you understand? Cross multiply. You are looking for X ATM. So X ATM will now be what? 700, this times this divided by this times this divided by this, 700 times 1 over 760. Hope you are following. It is very easy. 700 times 1 divided by 760, that is 0.9211, okay, ATM. Do you understand? That's how it's done. It's very easy. Based on temperature, it's simple as well. They can just say convert, for instance, let's say 20 degrees Celsius to Kelvin. What do? They've given you the degree Celsius already. You already know that degree Celsius plus 273 is equal to Kelvin. So 20 degrees Celsius plus 273 is equal to Kelvin. So 20 plus 273, that is 293 Kelvin. Do you understand? That is how it works. It's very, very easy, guys. So you can see how all of these conversions work. So let us progress to now talk about the gas laws, each of them. Okay, there are so many. We'll talk about them one after the other. Okay, guys, before we go over to the gas laws, here are some practice questions. Okay, do well to solve them. The first one, convert 200 centimeter cube to meter cube. The second, convert 500 torr to Pascal, and the last, convert 50 degrees Celsius to the Kelvin scale. So do that and make sure you provide the answer in the comment section. So we'll progress to the gas law. And the first of the gas law we'll be discussing in the course of this video lesson is the Boyles Law. So make sure you watch and make sure you're writing materials, because all of these things will help you greatly. Okay, guys, moving further, let us talk about the gas law. And the first of them we'll be discussing in the course of this video lesson is the Boyles Law. We have to understand that the Boyles Law is also called the Mariotis Law. This must be noted. We have to know that Boyles Law is also called Mariotis Law. And this law was discovered by a scientist called Robert Boyles. Okay, this is the man that discovered the Boyles Law. Okay, a scientist called Robert Boyles. So what was the concept of this man called Robert Boyles about the Boyles Law? He said something. He said that Boyles Law states that the volume, remember we talked about volume initially as a variable that describes gas behavior. The volume of a mixture of gas is inversely proportional to its pressure. Listen, the volume of a given mass of gas is inversely proportional. This is the proportionality sign. Is inversely proportional to its pressure. Whenever we are talking about inverse proportionality, it's going to be 1 over that particular variable. Do you understand? Inverse 1 over that particular variable. If it was direct, it is just that variable. 1 will not be included. 1 over will not be included. Do you understand? So Boyles Law states that, according to Robert Boyles, the volume of a given mass of gas is inversely proportional to its pressure, provided a parameter is made constant. provided temperature, which is another variable that describes gas behavior, provided temperature is kept constant. So they're telling us that for Boyles law to basically, be explained, temperature will be kept what? Constant. So let's walk through this expression, mathematical expression. So what do we do next? Very easy. What I advise you to do here is simple. We'll then, introduce a constant. That's what we'll do. We introduce a constant. So what do we do? It's going to be, okay, let's write that. Introduce a constant. And that constant you're introducing is K. So when we do that, we're going to have this. Please note it. Whenever we've introduced the constant K, this proportionality sign, which is this, will then change to something, which I'm about writing inside this bracket, will then change to something like equal to and K. Just watch. So it's going to be V. I want to remove this thing and impute equal to and K. Equal to K, okay, divided by P. Are you following me? It's actually easy. So then we cross multiply to make K subject of formula. So making K subject of formula, what do we do? P and V with times, dividing 1. Do you understand? So it's going to be P times V. So no need to put times, just PV over 1, which is still the same thing. If I say over 1, it is still, I say PV. Do you understand mathematically? So then this is the expression for what? The Boyles law. That is why Boyles law equation is simply P1 V1 is equal to P2 V2. Now, what does P1 mean? Okay, we have to know that anytime you hear 1, 1, 2, 2, 1 means initial, 2 means final. So P1, let's write out the parameter P1 V1. Okay, no, P1 P2 V1 V2, so to be easy for you to assimilate. P1 means initial, 1 means initial, and P is pressure. So P1 means initial pressure. P2, okay, means final pressure. Do you understand? Final pressure. Whereby V1 means initial volume. Whereby V2 means final volume. Are you getting me now? So all of these must be noted. I believe you already know the unit to which all of these parameters can be expressed. Pressure, ATM, mmHg, torr, bar, Newton per meter squared, Pascal, cmHg, as the case may be, volume, cm cube, dm cube, liters, milliliters, and meter cube. So all of these are the possible units to which they can be expressed. So with all of this said, let us solve practice question under the Boyles law. So after solving questions on Boyles law, I'm going to give you your own practice question so you solve and provide the answer in the comment section. If you find my lesson helpful, make sure you subscribe to this channel, share my videos with your friends. So let us progress. Okay guys, let us move over to the first practice question under the Boyles law. And I'll be arranging solving questions on each of the law in cases. So look at the first case, case 1 on Boyles law. It is when the parameters, which are the variables, okay, volume and pressure, because these are the two important variables on the Boyles law, okay, these are the two important PV, okay, we've said that already. When they are in the same unit, you see it. When they are in the same unit, how will you solve questions on that aspect? We have other cases which we'll be discussing, like case 2 after case 1. You see case 2 soon. So let's solve this question. It says a given mass of gas occupies a volume of 400 cm cube. That was my first volume. That was the first volume I saw. It's going to be ascribed 1. So solution on this, we are having our first volume V1 to be 400 centimeter cube, and I'm going to explain what I mean by they are in the same units. At 950 mmHg, which is the pressure, and it was the first, I told you how to identify the mmHg is pressure, cm cube is volume. 950 mmHg, that's the first pressure I saw. That's P1. So P1 is 950 mmHg, and calculate the volume occupied by the same gas. So they are now asking me, what is the second volume, V2, occupied by the same gas at 750 mmHg, which is my second pressure. Okay, at 750 mmHg, which is the P2, 750 mmHg. So then I said something. If temperature is held constant or kept constant, whenever I see that, remember when we stated Boyles Law, I said that the volume of a given mass of gas is inversely proportional to pressure, provided temperature is kept constant. Whenever you hear that word, that is a confirmation that the formula to use is the formula for Boyles Law. Whenever you hear if temperature is kept constant. And what was the formula for Boyles Law as derived? It is P1 V1 is equal to P2 V2. Very easy. Here is the formula. And what are they asking us to get? V2. And if you observe, are they not in the same units? Yes, the parameters will be in the same units. So this one that is in cm cube, we have to solve for the V2. What unit do you think this guy is going to be in? Cm cube as well. They are in the same unit. You see other cases whereby this will not be in unit, same unit with this. So will you solve like that? No. We'll get to that part. So what are we looking for? V2. Very easy. We are looking for V2. You make the coefficient of V2 subject of formula. So you make V2 subject of formula by dividing by the coefficient of V2. We are making this subject of formula. Let's divide by the coefficient of V2. What's close to V2? P2. Do you understand? P2, you can get now. So V2 will now be equal to what now? P1 V1 over what? P2, which is what? What's P1? What's the first pressure? 950 mmHg. Okay, times what is the V1? 400 cm cube. Okay, what divided by what is the P2? 750. Okay, 750 mmHg. So when we do all of this in a calculator, 950 times 400, answer divided by 750, that is 506.67. V2 will now be equal to 506.67 centimeter cube. This is the answer to the question. I believe you are following. It's extremely very easy. Okay guys, now if you are preparing to write the Jamb exam, any chemistry related exam, and you are finding chemistry calculations difficult, here is the chemistry masterpiece written by me. This book is very important for students preparing to write the Jamb exam, post-UTM exam, or even if you're in your first year in any university. This book is going to help you. The way questions are being solved here, that is how it is written in this chemistry masterpiece written by me. So if you're interested in getting a copy for yourself, do well to direct message me via the number in the screen. So guys, you can see how questions under this aspect are being tackled without stress. So let me give you one practice question so you solve and provide the answer in the comment section. Let us assume that the here was 300 centimeter cube and here was, let's say 800, something like that. Yeah, let's just work towards this. Okay, but this is very easy. Okay, you solve this and provide the answer in the comment section. So move over to the next case on solving questions under the Boyles Law, which is case number 2. Get ready. Okay guys, moving further, let us solve this question together. It is extremely very easy. And the question says, now we are on case number 2, which is when the parameters, which are the variables volume and pressure, are not in the same unit. You see in this question. So the question says 290 cm cube of a gas in a gas jar. That was the first volume I saw. So definitely it should be my V1. Okay, it should be my V1, which is 290 centimeter cube. Was observed to exert a pressure of this 700. That was the P1. That's the first pressure I saw. 700 mmHg. The volume occupied by the gas jar was increased to that value. Wow, that's the second volume. But watch for something. Watch out something. The initial volume and the final volume, are they in the same unit? No. Can you use them to solve like that? Don't do that. You won't get the correct answer. But we're going to work it out. We'll get the answer without stress. Okay? Was now increased to this value. Okay? Now they're asking us to determine the new pressure, which is P2. That's what they're asking us to get. Determine the new pressure. What do we do? It's extremely very easy. Okay, guys. First of all, we have to write out our formula, which is P1 V1 is equal to P2 V2. And what are we asked to get? P2. We divide both sides by the coefficient of P2, which is V2. Are you following me? So then P2 will now be equal to P1 V1 over V2. Hope you get. So you as a student, I know some persons will just say, okay, these are where the values given, then let me start imputing. Don't do that. Don't do that. Okay, just impute.
P1 is this, 700 times V1 is this, 290 divided by V2 is this. Don't do that. Make sure that they are in the same unit, the volume, okay? Because these were the two guys given to us. Make sure they're in the same unit. So that's why I taught you how to convert. So you can see that they gave us this one in this. So you can convert 290 to dm cube or 0.42 to cm cube. So look at what I want to do. You must make sure they're in the same unit in summary. So I want to convert this guy now, which is 0.42 dm cube to cm cube. How will I do that? Simple. Remember the conversion, which I taught you to be 1,000 centimeter cube is equal to how many dm cube? 1 dm cube. So we are looking for our answer in cm cube. So it's going to be x cm cube will not be equal to what they gave to us. Remember how I taught you 0.42 dm cube. That is why that particular first thing I said in this video lesson is very important. So x centimeter cube will not be equal to 1,000 times 0.42 divided by 1. Do you understand? You times like this. So 1,000 times 0.42, okay, 1,000 times 0.42, I'm having 420 centimeter cube. You can see now they are now equal, 420 centimeter cube. So I can now solve without stress. So in P1 is what? 700 times V1 is what? 290 divided by V2 is 420. Please, no, don't go and write 0.42, 420. So P2 will now be what? 700 times 290 divided by 420. That is 483.33. You know, the initial one was mmHg, so then it's going to be mmHg. Do you understand? So we've gotten our pressure to be this in mmHg, 483.33 mmHg. But watch. If you observe, they specified, make sure that the new pressure, you get it in ATM. So then the new pressure we've got it, make sure it's converted to ATM. How do you do that? How do you convert mmHg to ATM? We've done that already before. I've taught you that conversion. It is extremely very easy. So how do you do that? Let's quickly work it out here. I believe you're understanding it. So it's between mmHg and what? ATM. It's between mmHg and what? ATM. Remember the conversion between these two guys, which is 760 mmHg is equal to 1 ATM. So then we're getting an answer in ATM. What we got, which is 483.33 mmHg, would now be equal to x ATM. So what becomes x ATM? X ATM will now be equal to times, cross multiply, times 483.33 times 1 over 760 times divided by whatever you're having up here. So x ATM will now be equal to 483.33 times 1. 483.33 times 1 divided by 760. That is 0.64 ATM. Wow. This is the correct answer to the question. Here is the answer to the question. It's extremely very, very easy. Now, here is your own practice question. So you solve and provide the answer in the comment section. Let's say here was 0.39 dm cube. Okay, whereby here was 500 cm cube. Okay, so I think it's okay. So work it out yourself. Here remains the same. Work it out and get the answer. I've changed the value. Work it out and get the answer. Please work it carefully and get the answer. Actually very easy. Now let's get into the second gas law, which is called the Charles law. Okay guys, moving further, let's talk about the second gas law called Charles law. And first of all, we have to know that Charles law was discovered by a man called Jacques Charles. Okay, Jacques Charles. This is the man that discovered the Charles law. Are you getting me now? So on this, what does this law state? We have to know that the Charles law states that the volume, we are still interested with this variable because it describes gas behavior, which we've seen initially. The volume of a given mass of gas is directly proportional to temperature. Do you get? Initially for Boyles law, inversely, Charles law directly proportional to temperature, provided pressure is kept constant, provided pressure is what? Kept constant. This must be noted. So on this is actually interesting. Remember I said that we then walk through this mathematical expression by introducing a constant. Introduce a constant K. Okay, on this proportionality sign will be changed to what I'm about writing inside the bracket, and will be changed to equal to and K, which I've explained to you in Boyles Law. So let's work it out. V will now be removing this and putting this is going to be equal to K and T. Are you following me? So then let us make K subject. To make K subject to formula, you basically divide both sides by the coefficient of K, which is T. Are you following me now? So T cancel T. So what become K? V divided by T, volume over temperature. That is why the Charles Law formula is V1 over T1 is equal to V2 over T2. Remember, it has to do with initial volume. Okay, V1, T1, V2, T2, V1, 1, anything 1 initial volume, while T1 is initial as well, initial temperature, whereby V2 is final volume, and this is what? Final temperature. Are you following me now? And I believe you understand the conversions of the temperature we've talked about initially. So this is how this aspect works. So let's get into solving practice question under the Charles Law. Get ready. Now, if you find my video lesson helpful, make sure you subscribe to my channel and also share these lessons to friends. It's going to help you all improve. You have your class group chat. Make sure you send the link of this video to your class group chat and tell them to watch, because it will help them have a very great understanding on the state of matter, specifically gas laws. Okay guys, let's solve this question under the Charles Law. It's actually very easy. So let's solve together. Solution. We are still using the concept of, case 1 and case 2. Case 1 has to do with the parameters being in the same unit, and also we have questions on parameters being in different units. So please have that in your mind. It always works for all the gas laws. So here it says 600 centimeter cube of a certain gas. So they are telling me that the V1, the first volume I saw in this particular question is 600. So 600 centimeter cube. So then it's my V1 at constant pressure. Wow, when I see this, anything constant at constant temperature, I'll use the Boyles Law formula. At constant pressure now, I'm using the Charles Law formula, which is V1 over what now? T1 is equal to V2 over what now? T2. Have that in mind. Had a temperature of these. So this was my first temperature I saw, 49 degrees Celsius. Will I leave it this way? No, convert to Kelvin. And how do you do that? You simply add 273 to this, which is degree Celsius value. So you get your answer in Kelvin. So let's do that before we just progress. So 49 degrees Celsius plus 273 is equal to Kelvin. Okay, that is 322 Kelvin. K. Okay, we can just stop there by saying K. Now, at what temperature? They are not asking us to get the second temperature. At what temperature will, in Kelvin specifically, your temperature should be in Kelvin, will it occupy 800 centimeter cube? So V2 is what? 800. So if you observe, this particular question is on case 1, the same case 1, which has to do with the variables being in the same unit. If it was in different units, what will you do? Convert. Do you understand? Don't just solve. Don't solve in different units. You won't get it that way. Convert. So what do we do next? Let's get our answer. It's simple, like A, B, C, B. So then we are looking for T2. Let's make T2 subject of formula. T2 making it subject, we are having T1 times V2 divided by V1. T2 will now be equal to, hope you understand how I got T2. Simple. What's T1 again? T1 is it 49 or 322? 322 times what's our V2? What's the V2? V2 is 800. Okay, divided by what's our V1? What's our V1? 600. 600. So what becomes the T2? T2 will now be equal to 322 times 800 divided by 600. That is 429.33 Kelvin. So this is the answer to the question. I believe you understand how it works. It is extremely very easy. Now, as earlier said, this particular textbook has all the calculations in chemistry, okay, strictly chemistry calculation, ranging from those calculations in atomic structure, like determining numbers of protons, electrons, neutrons, all of those calculations dealing with atomic mass numbers, as the case may be, down to chemical equilibrium. It has so many calculations in it: electrolysis, stoichiometry, and so on, solubility. There are so much. So this book is a very important book for you for your chemistry success. So make sure, if you're interested getting it, make sure you do well to direct message me via the number in the screen. Okay, so let us progress to another gas law. Okay, and this time around I'm going to talk about the Graham's law of diffusion. This law gives so many student issues, but in the course of this video lesson, I believe after watching it, you'll be able to understand the rudiments of this gas law called the Graham's law of diffusion.
Okay guys, moving further, let's move over to this new gas law called Graham's law of diffusion, or effusion. It's actually very easy. Before we talk about, actually this law was discovered by a man called Thomas Graham, okay? But before we will talk about the law, what it states, we have to understand what this terminology diffusion and also effusion means. It's very, very important. You know, diffusion and effusions, they are properties exhibited by gases as well. Like we talked about random motion and the rest. This is another property exhibited by gas molecules, diffusion or effusion. Now, let's take an instance. Here is a container. Let's say we have this container, and this container is made up of different gases. For instance, okay, this is the opening of that particular container, and made up of like 3 gases: gas A, gas B, and gas C. And you know that gases, they don't really, the particles of gases are not held together. They are loosely packed. That means they tend to move in an irregular manner, which means that they undergo random motion. So let's say we have the gases embedded or inside this container, and the orifice of this container is opened. Listen, the movement of these gases from where they are found to the surrounding environment. Let's say these gases are now moving. Gas A moved, gas B moved, and gas C moved. Because they move through the orifice from the region to which they are found, or they are highly concentrated, to the environment, we simply call that diffusion. So let's bring it into the right term. So I can as well say that diffusion is the movement of particles, which are all of these, A, B, and C, from a region of higher concentration to a region of lower concentration. This is what we call diffusion. For instance, say you take a deodorant and then you spray that deodorant. Okay, let's say you spray the deodorant inside this particular room I'm in. Do you think, though the smell of that deodorant will actually diffuse to other environments, but I want to ask you a question: the region to which that deodorant was sprayed compared to the region where it was not sprayed, which one will the deodorant will felt more? It will felt in the region to which it was sprayed. That's the higher concentration. So the deodorant then moved to a region where they will be found in a low concentration. So diffusion has to do with the movement of gases, particles in general, from a region of higher concentration to a region of what? Lower concentration. That's what diffusion means. But effusion now, in effusion, these gases are moving. Let's say it's sealed. This container is sealed. They are moving through a pinhole, or they are moving through a tiny hole. So these gases are actually forcing themselves to move through this tiny hole. This is what we call effusion. Do you understand? So effusion and diffusion are the same. Effusion is simply the movement of these gases through a tiny hole or a pinhole, but diffusion is just moving freely. Do you understand? But it's still region of higher concentration to a region of what? Lower concentration. This is what the concept, or this is how the concept of diffusion and effusion works. So now let's talk about Graham's law of diffusion. What does this law state? It's actually very, very easy. So let's move on. Okay guys, it must be noted here that Graham's law of diffusion or effusion of a gas states that the rate, now we are dealing with rates, very important. Rate is a very important parameter here now. The rate of diffusion or effusion of a gas is inversely proportional to the square root, inverse 1 over the square root of its molecular mass. So this must be noted for Graham's law of diffusion. Graham's law of diffusion states that the rate of diffusion of a gas is inversely proportional to the square root of its molecular mass, not just square root of its molecular mass, or even square root of its density. So for Graham's law of diffusion, it can be in two formats, being relating rate and molecular mass, or relating rate and density. Hope you are following me. Please, it's actually very easy. Watch carefully. Now, if we were to work this mathematically, listen. If we were to work this mathematically, we are to have the relationship between rate and root of molecular mass to be this. R1 divided, on these gas laws, we describe, gases, not just one. That's why it's actually R1 and R2. So R1 over R2 is equal to root of M2 over M1. This M signifies molecular mass. Hope you are following me. If we were to work it mathematically, if I were to show you the mathematical, the working, the derivation, this is what we will arrive at. Do you understand? The derivation here is not really important. Knowing the formula is very important, okay? So if we were to work this through the same format, we have to have something like R1 over R2 is equal to root of M2 over what? M1. This must be noted. Okay guys, moving further, this word or this terminology rate, I have to tell you guys what it means. Mathematically, you have to know that rate is simply volume of that particular gas, volume of a gas per time. Per means divided by time taken of that gas to effuse or diffuse. I believe you already know what diffusion and effusion mean now. Effusion, you're moving through a tiny hole. Diffusion, just moving freely. But you're moving from a region of what now? Higher concentration to a region of what? Lower concentration, using the deodorant scenario. Okay, so that's the point. Understanding rate and volume now is very, very important. Okay, now please watch out something, because on this particular Graham's law of diffusion, I'll be giving out different formulas and solving questions. So this formula is very important. So in general, how many formulas have I given you now? 3. I've given you in this first one the relationship between rate and molecular mass, and you can see how it is. No, it is very important. The relationship between rate and density. Sorry, here should be density, D2, okay, over D1, okay, D2 over D1. And the relationship between rate, relating volume and time. So note this formula is very important. They might ask you a question on that rate, okay? I'm going to solve questions on it. So I have to say something. You have to note that rate in this formula, you can see that rate and volume, are they not in the same line? Note something. Rate and volume are in the same line. This will tell you that rate and time, they are not in the same line. You can see that rate is up, time is down. Note something. I'm just using this scenario to make sure that you understand it very easily without you cracking your head. So rate and volume, both of them are directly proportional to each other. Please note it. Rate and volume are directly proportional to each other. Whether rate and time taken or just time, they are inversely proportional. I know why I'm saying this. It will help us. Note it. Rate and time, they are what? Directly. Rate and volume, because they are in the same line. This one, they are dividing, like rate and this one. Mathematically, you understand that rate and time, they are inversely proportional. Whereby rate and volume, they are directly proportional. Hope you understand my point. It will help us. Just note it. So after all of this said, let us now bring out so many formulas under the Graham's law of diffusion. It is very easy. Please put these two things in your mind, because that's what I'll start from in my explanation. Alright, so if you are finding my video lesson helpful, make sure you subscribe to my channel and also share these lessons with your friends. So let us progress. Okay guys, moving further, let us do some derivations or some other formulas under the Graham's law of diffusion. They are very easy. I believe you already have this in mind, that rate and volume, they are directly proportional. Rate and time, they are inversely proportional. Please have that in your mind. So then I want to relate something. I want to relate rate, not just rate. I want to relate volume, rate, volume, and molecular mass together. when I do this, what becomes my formula? Very easy. Once I'm done, I'll give you your own to try. It's very easy. Look at it. I want to do something. Rate already. Where do you know that this is how it's written? R1 over R2. Okay, R1 over what? R2. Now, what's the relationship between rate and volume? Is it not directly proportional? It means that when rates increase, volume increase. See, it's going to be times V1 times V2. This is just a smart way to understand some concept on this aspect, because they'll give you questions with different parameters, so you have to know exactly the formula to use. That's what I'm. So you understand it very soon. Just hold on. Is equal to molecular mass. Remember, this is how it's always written, does not change. M2 over what? M1. If you observe, I said that rate, volume, they are directly proportional to each other, meaning that if rate increase, volume will increase. If rate is 1, volume will be 1. If rate is 2 here, volume will be 2 here. Do you understand? So I want you guys to do something for me in the comment section. Relating rates, not just rates. I want to relate rate, time, and molecular mass. Let's do this together. Everybody in the comment section. Simple. So we already know that rate and time, they are inversely proportional. Rate and what? Time, they are inversely. So it's going to be R1 times, we want to relate it with time. When rates increase, time decrease. If rate is going up, time will come down. So it's going to be T2 over R2 times what? T1. Hope you understand. Rate is increasing, time is decreasing. Do you understand? Do you understand what I'm saying? It's going up, so it's coming down. Relative with molecular mass does not change, which is what? M2 over what? M1. Do you get? Hope you know that we can actually remove molecular mass and write density here. Do you understand? And put a D2 over D1. Do you understand what I'm trying to say? It's actually very easy. So with all of this, I will still give us some few formulas so we can start solving questions under the Graham's law of diffusion. It's actually very easy. Make sure you subscribe to my channel and also share these lessons with your friends. Okay guys, let's say for instance, we are relating now, or remove rate, just volume and molecular mass. Just these two guys. It's simple. Just assume that rate does not exist. Remove your rate and just write it where it is here. So it's going to be volume 1 over volume 2 is equal to root of M2 over M1. You don't have to cram too much. Simple. You don't have to stress yourself. And you know that if here was density, hope you know what it is. If here was density, this over D1, the same thing. Hope you get. But let's say for instance, we are relating time and molecular mass together. What do we do, everybody? Simple. You already know that time is T2 over T1. So it's going to be T2 divided by T1. Still write it the way it is. Hope you understand. It is extremely easy. These are secrets to understanding this law called the Graham's law of diffusion. There are so many other formulas in my chemistry textbook, which is the chemistry masterpiece, which will help you improve greatly. Okay. So as earlier said, make sure you get a copy for yourself because it's extremely very important, irrespective of where you reside. Chemistry masterpiece can get to you. All right. So moving further, with all of this said, let us now start solving practice question under the Graham's law of diffusion. Okay guys, moving further, let's solve this question together. It's actually very easy. Okay, so here is the first practice example, which says given the rate of diffusion, they've given us the R, which is rate of diffusion of a gas X to be this 200 centimeter cube per second. Actually, okay, let me quickly say this. Remember, okay, I will say it as we progress. Just hold on. It's very easy. What is the volume? Okay, because I did not talk about how to get these units. Okay, but it's simple. I'm going to talk about it now. What is the volume of X? They're asking us to get the volume of X, that it will. What volume of X will it take 1440 minutes of that particular gas to diffuse through an orifice? It's very easy, which is gas X. Now, how do we solve this question? It is relating to rates. They are asking me to get volume. They gave me time, but the time was expressed in, minutes. Please watch. Simple like ABCD. What is the formula for rate? As explained initially, rate is what? Volume of the gas over time taken for that gas to diffuse. Now, it's very easy. What are the possible units for volume? One of them is centimeter cube, cm cube. And what is the basic unit of time? Seconds. So mathematically, the unit of rate is going to be centimeter cube slash seconds, which is per seconds. That is why the unit of this rate was this, centimeter cube per seconds. Are you getting me now? Your rate must always be in per seconds. So if you observe, they give us time in minutes here. Can we use it to solve? No, we have to convert time from minutes to seconds. And how do you do that? You have to know the conversion factor. How do you convert minutes to seconds? That's what you ask yourself. To convert minutes to seconds, okay, first of all, you have to understand that 60 seconds makes how many minutes? 1 minute. So then the x seconds which we want to get now, because this is what the time should be in, is equal to what they give to us in the question, 1440 minutes. Hope you understand this simple conversion, x. So cross that line. So what become x seconds? 60 times 1440, which is 86,400. So x seconds is equal to 86,400 seconds. Are you following me? So what becomes the, what do you call it now? Now, first of all, what are they asking us to solve in this question? They're asking us to get what? Volume. That's what the question is asking us to get. Volume. So you making volume subject of formula. What do we have? Volume we are making subject is going to be rate times time over 1. Hope you know this. Volume will not be equal to rate times time divided by 1. That's it. Volume will not be equal to, what's the rate? According to the question, 200. Okay? 200. Okay? Times time. What's the time? Now we've calculated. We are not using 1440, but rather we are using the 86,400. 86,400. Hope you get. Divided by 1. What becomes our volume? Now let's write the way it was written. Here is centimeter cube per seconds. Time 86,400 seconds as well. Hope you know. Seconds will cancel seconds, remaining just centimeter cube. So it's going to be 200 times 86,400. That is, volume will not be 172800000. What's remaining? Seconds. So this is the answer to the question. Is extremely very easy. Okay, what you have to do, just look at the question, know exactly what you're asked to solve for, and get the answer without stress. So here is your own practice question. So you solve and provide the answer in the comment section. Let's say the volume given was 300, or let's reduce it to like 100. Okay, and then the time was in hours this time around, and let's say they gave us it to be like 2 hours. Make sure you know how to convert hours to seconds. How do you convert hours to seconds? You times by 260. 60 times 60 times that 2. You times the number they give to you for hours with 260. 60 times 60. Hope you understand. It's very easy. Okay, I have to just show you all of these. But to convert from hours to seconds times by 260, to convert from minutes to seconds times by 160. No, I don't mean 160. I mean times by 160. 60. Do you understand? Why for hours to seconds, as seen in this practice question, give it to you, it is times it by 260. 2 times 60 times 60, you get your answer in seconds, and then get whatever you are asked to solve. It's simple, which is volume. Okay, so let's get into the next practice example. Okay guys, moving further, let's solve this question together. It's extremely very easy. It says, if 465 centimeter cube of SO2, hold on. In this Graham's law of diffusion, majorly we deal with like 2 gases. Okay, just note it. We deal with how many gases? 2 gases. So 400. So listen, this was my first volume I saw. It is 465 centimeter cube, of which gas? SO2. Have that in mind. If this gas, this 465 centimeter cube of SO2 can diffuse through a partition in 30 seconds. So the time T1 is 30 seconds. It's simple, very easy, like ABCD. How long will an equal volume of that same gas? So let's say this V2 now, they say it has equal volume. 465 again, equal volume. It has the same volume, equal. Volume of H2S. How long will it take volume of H2S to diffuse through the same partition? So they say how long time will it take an equal volume of H2S to diffuse through the same partition? That's what this is the parameter. These are the parameters we need to solve this question. It's very easy. Now, if you observe in this particular practice question, we were given the compounds. The first one, SO2, this was the first compound I had. SO2 was the first compound. So, okay, we have to pull that. This is SO2. And this is H2S as well. Please watch. It's simple. SO2 was the first compound. So it should be the M1, which is the molecular mass of the first compound. Hope you know M1 means molecular mass of first compound, whereby M2 was the second mentioned, so it should be the M2. Whereby H2S was the second gas mentioned, it should be the M2. Hope you understand these things. They're simple. Okay, so let us calculate the molecular mass of each of them. How do we do that? It's relating SO2. This is SO2. How do we get our molecular mass or the molar mass? Molar mass, okay? It's going to be sulfur atomic mass is 32. You have to know that. Oxygen atomic mass is 16. We have 2 of it. 16 times 2. So we have 64 grams per mole. Hope you know this. Because 16 times 2 is 32. 32 plus 32, that's 64. Hope you are following me. Whereby H2S is this molecular mass is equal to hydrogen atomic mass is 1, something you should know, times 2, plus sulfur atomic mass is 32. So 32 plus 2, because 1 times 2 is 2, that's 34 grams per mole. Hope you're following. Hope I'm not too fast. Okay, it's actually easy. So molecular mass of the first compound is 64 grams per mole, whereby molecular mass of the second compound H2S is what? 34 grams per mole. So if you observe here, we are relating different parameters. Please watch. In this particular question, it relates volume, it relates time, and then molecular mass. Volume, time, molecular mass. Was it simple? It is V1. Remember, volume and time, they are not directly proportional. When we are having V1, what should follow is T2. We said that. Check your formulas. T2 over what should be down? V2, what should be down? T1. Hope you are following me. And you already know that molecular mass is always M2 over M1. Hope you are following. We've said this. We've derived this formula. If here was density, D2 over D1. Simple. Do you understand? That's how it works. So moving further, what do we do next? Impute. And what are we looking for? Time taking for the second gas to diffuse through the same partition. We are looking for T2. So V1 is 465 times time T2 divided by V2 465, because they are of the same gas. So we are able to cancel this. We are supposed to even cancel this self. Do you understand? They will cancel each other, but let's just leave it. T1 is 30 seconds. Is equal to root of M2. What's M2? M2 is 34 over 64. Hope you are following me. So what do we do first of all? My advice here is to do the square root of this. So square root of 34 divided by 64, that is 0.73. So 465 times T2 over 465 times 30 is equal to 0.73 divided by 1. Cross multiply. Hope you are following. This will cancel this, remaining just T2 and over 30. Hope you are following me. So we are having something like this. This will now give us T2 over 30 is equal to 0.73 over 1. Okay, please pardon the way, hope you're understanding. So let's make T2 subject. To make T2 subject, is going to be T2 is equal to 30 times 0.73 divided by 1. So what are we having? 30 times 0.73, that is 21.9. T2 is 21.9 seconds, approximately, which is approximately 22 seconds. That's the time it will take the second gas to diffuse. Hope you are understanding my point. It's actually easy. Okay, there are different ways to understand this particular concept. Okay, I believe you got how it was solved. Okay, so let us progress. Okay guys, what will happen now is I'm going to give you your own practice question, so you solve and provide the answer in the comment section. You know, I always give you your own practice question. Let's say here was increased to 500 and here was this time, let's say it was increased to like 40, and then it remains the same. Every other thing should remain the same and equal. No, how long will it take? Let me change it. It should not be equal this time around. Let's say here is 300 of this 300 centimeter cube. You know, it was equal before, so that's why we cancel them. Okay, I don't want to just tell you that, okay, since it was equal, I want to show you that you can see that it's actually equal. Do you understand? I don't want to just do it initially so that you get the picture of what I'm saying. So that is that for that. So let's get into another gas law. Okay, if you are finding my video lesson helpful, make sure you subscribe to my channel and also share these videos with your friends. Okay, so let us progress.
Okay guys, let's get into the general gas law simultaneously with the gas equation. Very easy. Now this you must note, the general gas law is made up of two laws, which include the Boyles law, which we've talked about, and the Charles law. addition of both of them gives us the general gas equation. Very easy. What's the Boyles law? What does it state? Volume is inversely proportional to pressure and directly, now Charles, what does it state? Volume is directly proportional to what? Temperature. So this is same volume. I can't write volume again. So it's directly proportional to temperature. For Boyles law, volume is inversely proportional to pressure. For Charles law, volume is directly proportional to temperature. So with this, bringing them mathematically, what do? Remember, this will change to equal to and K. Hope you know that. So we're having something like volume will now be equal to K over P, whereby this will change to times. Are you following me? So times T. So we are having something like V is equal to KT over P. So making K subject to formula, what are we having? K subject P times V divided by T. Yes. This is why the general gas equation formula is simply this: P1 V1 over T1 is equal to P2 V2 divided by T2. That is how the equation is. Okay, now we'll solve question on this, but let's not quickly talk about the ideal gas equation. On this, it is made up of three. The Boyles law, listen, the Boyles law, the Charles law, and what we call Avogadro's law. Avogadro's law. Note this. Now, Boyles law, you already know what it states. You already know what this one states. And this one, for Avogadro's law, it says volume is directly proportional to numbers of moles. Note this. Volume is the what? Directly proportional to numbers of moles. That's what it talks about. That's the summary to that law. Or it's an hypothesis, actually. It's not yet a law. So we call it Avogadro's hypothesis. Okay, still being worked on to be a law. So Boyles law, you already know that volume is what? Inversely proportional to pressure, and volume again is directly proportional to temperature, and volume again is directly proportional to numbers of moles. Hope you know. So we are having volume, you do your normal, which is volume is equal to K over P. You already know this. These two will change to times. Okay, times T times N. Hope you are following me. It's very easy. Let us make K subject to formula. It's going to be P V, yes, P times V divided by Tn. Hope you are following me. It is extremely very easy. You know, when you cross multiply here, you're gonna have something like PV times 1 is equal to NT and K. Hope you understand now. So we can rewrite it to be just PV, because times 1 is nothing, is equal to what? NTK, whereby this our K will be changed to a symbol arrow, because we'll work on that symbol very soon. So we're having PV is equal to NT arrow. But if we want to structure it well, the ideal gas equation is PV is equal to what? N arrow T. Are you following me? This is your ideal gas equation. PV is equal to N arrow T. Simple. It's actually easy. Practice makes perfect. Are you following me? So this must be noted. We've derived the ideal gas what? Equation. Meanwhile, on the Dalton's law of partial pressure, that particular law, which is a gas law, I already have a video lesson on that particular aspect. The link to that particular video will be in the description, so make sure you watch that particular video law, okay, called the Dalton's law of partial pressure. And as well, even the exact law of combining volume, I already have a video on that aspect. The links will be in the description of this particular video lesson, so that you know that all the laws have been treated. And also we have a law called the pressure law, also called Hamilton's law. I already have a video on that. The link, I'm still going to put it in the description of this video, so that we know that the general gas law and the ideal gas equation, and then you go watch the other laws on my channel, because they will help you improve greatly. Okay, so let us progress by solving question under the general gas law. Okay guys, moving further, let's solve this particular question under the general gas law. It's actually very easy. Remember, we already derived the formula on the general gas law. And what is the formula? It is P1 V1 over T1 is equal to P2 V2 divided by T2. So on this, let's read our question. It says a gas occupies a volume of 5 centimeter cube. That was the first volume I saw, so it should be 5 cm cube at 18 degrees Celsius. 18, that's temperature T1, 18 degrees Celsius, right? Yes. And 0.9 atm, that is my first pressure. I believe you're already familiar with knowing all of the symbols. their units, okay? So you just know which is this and which is that. So they say calculate the final volume. They say we should calculate final volume V2, okay, of the gas if it occupies 1 atm. That's P2 1 atm at T2 4 degrees Celsius. Simple. First of all, you have to convert your temperature to Kelvin, which is 18 plus 273. You already know what to do here. 18 plus 273, that's 291 Kelvin, and 4 plus 273, that is 277 Kelvin. Hope you know how I got this. You added 273 to the values. We don't solve using degrees Celsius like that. So then what next do we do? We are looking for volume. Let's make volume subject formula. We are looking for volume. So make volume subject formula. We are having V2 will now be equal to everything here dividing the two other guys here. So it's going to be P1 V1 times T2 divided by, okay, P2 times T1. V2 will now be, because what's our P1? What's P1? What's P1? 0.9. 0.9 times V1. What's V1? 5 times T2. What's T2? 277 divided by P2. What's P2? 1 times T1. What's that one? 291. So V2 will now be equal to 0.9 times 5 times 277 times 1. Okay, 277. Okay, answer divided by 1 times 291. That is 4.3 centimeter cube. This is the answer to the question. Yes! This is the answer to the question. It's extremely very easy. I'm going to give you one practice question. So you solve and provide the answer in the comment section. Let's say the temperature was changed to like 50 degrees Celsius. Volume was, let's say, 30 degrees Celsius. And this temperature was given to be, let's say, 300 Kelvin. So how do you solve question under this aspect? It's extremely very easy. Meanwhile, under this law called the iodic gas equation, I already have a video on this. Okay, I just realized I've created a video on the iodic gas equation. So I'm going to still put the link down in the description of this video, so you know that the other laws have been tackled. So do well to go watch all of these lessons. They will help you improve greatly. Now, come to the end of this video lesson, and if you find my video lessons helpful, make sure you subscribe to my channel, share my video with your friends, like this video, give this video a like so that other person can have the opportunity to learn as you're learning right now. Thanks for watching.